Hi guys! So, this unit is all about sequences and series. So, this first section is all about sequences. So, an infinite sequence is exactly what you think it would be, only they put it in a really complicated way. It's a function whose domain is the set of positive integers, and a sub 1, a sub 2, a sub 3, blah 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 are the terms of the sequence. So we usually give the terms, we number them. So 1, 2, 3, 4, 5. So that's why the domain is the set of all positive integers. A finite sequence is the same sort of situation, only it's the first so many positive integers. So that means that our sequence has an ending. So it doesn't just go on and on and on forever. Some of them will just, have 5 terms or 12 terms or a billion terms or whatever it happens to be. So we want to write the first 4 terms of the sequence. So it says that a sub n equals 3n minus 2. So what n stands for in this situation is the number term it is. So to get my first term, I would have to plug in 1. So 3 times 1 is 3 minus 2 is 1. To get the second term, I'll plug in 2. 2 times 3 is 6, minus 2 is 4. To get the third term, I'll plug in 3. 3 times 3 is 9, minus 2 is 7. To get the fourth, I'll plug in 4. 3 times 4 is 12, minus 2 is 10. Dot, dot, dot. So it's not that terribly difficult. Now, when we have something like a sub n equals 3 plus negative 1 to the n power, this is something kind of fun that's going to happen. We know that if we take negative 1 to a even power, it's going to become a positive 1. And we know that if we take negative 1 to an odd power, it's going to stay a negative 1. So our sequence is just going to switch between 2 numbers forever and ever and ever. So if we plug in 1, that means I have negative 1 to the first, so that's just negative 1. So 3 minus 1 is 2. If we plug in 2, negative 1 squared is 1. 3 plus 1 is 4. If we plug in 3, negative 1 cubed is negative 1. 3 minus 1 is 2. If we plug in 4, negative 1 to the fourth is positive 1. 3 plus 1 is 4. So as you can see, it'll just keep bouncing back and forth, 2, 4, 2, 4, 2, 4, 2, 4. Same sort of thing is happening over here. So let's plug in 1. Negative 1 to the first is negative 1. Then we'll plug in 1 in our denominator, so 2 minus 1 is 1. So that's negative 1 for that first guy. Now we'll plug in 2. So negative 1 squared is positive 1. 2 times 2 is 4, minus 1 is 3. So my next term is 1/3. Next we will plug in 3. So negative 1 cubed is negative 1. 2 times 3 is 6, minus 1 is 5. So my next term is negative 1/5. Then we'll plug in 4. Negative 1 to the fourth is positive 1. 2 times 4 is 8, minus 1 is 7. So my fourth term is 1/7. And maybe that sequence goes on and on forever. So plug it in, getting those terms, easy peasy lemon squeezy. Now we're going to flip it around. Now we're going to give you guys a sequence, and you need to tell us A lot of times it's called the explicit formula. Sometimes it's called the expression for the apparent nth term. Find an equation for the nth term. There's lots of different ways that people are asking, hey, what's the rule for this sequence? So here we go. What I think is helpful if you're having trouble trying to figure it out is to label each of the terms 1, 2, 3, 4. So then you can kind of think about, okay, what's happening to each of those numbers? So for 1 to get to 1, there are lots of things could have happened. For 2 to get to 3, we could have added 1. For 3 to get to 5, and for 4 to get to 7. Okay. So let's see. I'm sitting here thinking, if I were to double each of those numbers and subtract 1, that's where I end up, right? So 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 3 times 2 is 6, minus 1 is 5. Yeah, there we go. That's what we want. So this formula is going to be a sub n equals, we knew we had to double our term number and then subtract 1. Okay, let's try over here. So I got term 1, term 2, term 3, term 4. Okay, so 1 and 2, 5, all of these seem like they're one off from something really important connected to those numbers. Do you see what I'm saying? 2 is 1 more than 1. 5 is 1 more than 4. 10 is 1 more than 9. 17 is 1 more than 16. See what I'm getting at now? If we take our term number and square it, and then we add 1, we'll end up with that sequence. So I think it's helpful sometimes to number it. Sometimes if you're having a lot of trouble trying to figure out, is that what really is working here? Sometimes I just leave it, come back to it with a fresh set of eyes, and it's a little bit easier to figure out. Okay, so now let's talk about what a recursive sequence is. So a recursive sequence is a sequence where all of the terms are defined using previous terms. So a really famous one is a Fibonacci sequence, which we'll talk about here in a minute, and I'm going to give you some suggestions on some watching that we would be watching this YouTube video in class. I swear, I love it. Anyways, I'll give you a suggestion in a minute. Anyways, so we want to write the first 5 terms of the sequence, defined recursively as follows. A sub Bonnie, a sub 1 equals 3, and a sub k equals 2 times a sub k minus 1 plus 1, where k is greater than or equal to 2. Ugh. Basically, here's what they're saying. Here's the first term. You're going to take that term, double it, and add 1 to it. That's how you get the next one. Then you're going to take that term, double it, add 1 to it. That's how you get that term. So it told me that I'm supposed to start off with 3. 2 times 3 is 6, plus 1 is 7. 7 times 2 is 14, plus 1 is 15. 15 times 2 is 30, plus 1 is 31. 31 times 2 is 62, plus 1 is 63. And that will go on forever. So that's what a recursive formula is, or a recursive sequence. You go back to previous terms that you had to find terms later on in the sequence. Like I mentioned, one of the most famous recursive sequences is the Fibonacci sequence. It was first written about by Leonard of Pisa, or Fibonacci. He is quite the dude, came up with a lot of stuff. And where the Fibonacci sequence comes from is really interesting. So basically, here's what the Fibonacci sequence is. You get the next term by adding up the two terms in front of it. So we just start by saying the first term is 1. There's nothing in front of it, so nothing plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, so on and so forth. Okay? So what I suggest you do is go on to YouTube, and search Weihart Fibonacci, just to get you started on some information about the history of where the Fibonacci sequence first came from, and bunnies, and it gets into it. Anyways, I suggest you first watch the SciShow. It's only 3 minutes and 20 seconds. Gives you a whole bunch of information. Talks about Leonard of Pisa being awesome because he's the one who introduced Arab numerals into the European world. Otherwise, we would still be using Roman numerals. We love Arabic numerals. They make our life so much easier. Okay, first there's that. Then, oh my God, then you need to watch Weihart, Spirals, Fibonacci, and Being a Plant. You need to watch this. It is awesome. Fibonacci numbers are all over the place in nature. I learned so much about biology watching this. I loved it. I really think you should devote some time to it because I think it's well worth it. Another thing you might want to do is she talks a mile a minute. So please slow that speed down if you're having trouble understanding her. There's a lot of information in there that is really cool and really interesting, and stuff that I think you really will enjoy, that we're starting to really get into the beauty of math and how math really describes our world in so many different ways, and I want you to have an appreciation for that. So please take some time to watch those. I think it is well worth your time. Okay, we'll practice this tomorrow. I really miss you. Bye, guys.